So here are the four resonance forms for this. This is called phenoxide. And phenoxide is going to be a weaker base or a stronger base than the cyclohexoxide compared to the other one. This is going to be a weaker base because we can delocalize some of the negative charge against it here into the ring. And so the ring has an electron withdrawing effect compared to cyclohexane, which didn't have any possibility of doing that. Now, this is resonance delocalization, but we can also have an inductive effect because each of these sites here consists of a hydrogen, which isn't drawn here usually. The hydrogens aren't drawn because to save time, that's all. Here, but there's a hydrogen on each of these. And what we do is we label the positions here on the ring because we can also have an inductive effect as well. So it depends on, you see there's a negative charge here, there's a hydrogen here, and so we're still okay. We're still obeying the octet on this carbon. We have 3 single bonds and 1 lone pair. However, what if we change the hydrogen to some other atom? So if we put an electron-rich group there, is that going to help delocalize the charge or the opposite, or concentrate the charge? So rather than a hydrogen, we put some other, like an electron withdrawing group or an electron pushing group on there. That's going to change how this is going to behave. And so in that sense, we're going to label these positions. These 2 positions are called meta. These 2 positions here are called ortho. And this position here, there's only one of them, is called para. And so we have meta, ortho, and para positions here. When you look at the negative charge, what carbons does it go on? When we look at the negative charge here, what position is that? Meta and ortho and meta. And so in this case here, it doesn't go on the ortho positions or the ortho meta pair. Did I get that right? Yeah. Meta. Whichever. I have to back that up. And so let's take a look at another example here. Well, I think orthometa pair, sorry. But let's take a look at some other examples here. From the book. Professor, yes.
If we have something larger than a benzene ring, would we have different names besides meta, para, and ortho? Or would we keep the same, just expand what they cover?
If you have something larger than a benzene ring, they have different, like you're talking about 8 carbon or something?
Yeah.
Rather than 6 carbon? Yeah, they'll have different names. Different positions. Benzene ring is so common that
it gets special names.
You can have multiple benzene rings linked together.
With the same naming scheme?
No, it's different. I mean, within the ring, it's the same meaning.
I have 6 benzene, make 8 benzene, benzene.
You have different ones, and I'll show you some.
You would still make the same, it's still benzene. There's just more benzene on your benzene. Oh, that's terrifying. If you know what a fractal is, you know what I'm getting at when I say benzene, benzene, benzene.
The third derivative.
A lot of benzene. Just take the 4th derivative.
All right, so we look at these two acids here. Phenol and, orthometapara. So orthometapara. So can you fix that on your notes? And orthochlorophenol. Which one should be stronger? And why? So would you expect the pKa? The pKa is just the power. We've been looking at Kas. But if we just look at order of magnitude, this is going to be the pKa. The pKa actually contains a coefficient as well. But basically, the smaller the pKa, the stronger. The bigger the pKa, the weaker. So what would you expect? Orthochlorophenol is stronger. That's correct. Why?
Because the negative charge is going to spend more time in the ring and in the ring,
Yeah.
making the hydrogen more positive.
All right. Basically, there are two reasons. One, we expect increased polarity of the OH bond. So the polarity is going to be greater. It's going to be more attractive for a base. And then number two, the stability of the product is going to be better. Because if we have rather than a hydrogen here, this is not meta, this is ortho. This is meta. This is still parent. If instead of putting a hydrogen here, we put a chlorine here, then that's going to be an inductive delocalization too. So not only are we going to have resonance delocalization, we're going to have this inductive effect as well. And so that's going to help stabilize the product. And so having a orthochloro is better for stability of this base. Does that make sense? Pretty much? Okay, good. Also, having a parachloro will make it more stable as well. Meta, not as much, right? Because meta, the negative charge doesn't land on the meta. I mean, and so to answer this question here, what do you expect the power? Now, the power function is the negative. It's to the negative power. So this is 10 to the negative 10. And so we would expect the pKa, the acid strength, to be greater. If it's greater, it's going to be lower than 10. So we're going to say it's going to be less than. making it a stronger acid. Okay, this goes both ways, not, because we're looking at base strength here. And so we're going to back out here and we're going to take a look at this. Let's compare this. This is phenyl, the substituents of phenyl on an amine. So we call this phenylamine, or it has a common name called aniline. Here. And then this is cyclohexyl substituent on amine. So we just call it cyclohexylamine. Phenylamine or aniline. Okay, which of these two is a stronger base? Cyclohexylamine or aniline? And so we're cyclohexylamine. This is much stronger. How many orders of magnitude? How many powers of 10 is it? It's 6 powers of 10.
About
A million times stronger base. Why is this one a million times stronger than that one?
it is not double bonded in carbon.
Has less resonance.
Yeah, so what we want a good base on the nitrogen should have two things. It should have lone pair and what makes a good base? What's the first thing we look for in a base? Charge. So we want greater charge, negative charge density, right? Bases are negative. Here, the delta minus is localized. There's no charge. Nitrogen's neutral, right? There's no charge on it, but it has a delta minus. And the delta minus is going to be concentrated, that is, the electron cloud is going to be concentrated in nitrogen here and not delocalized. In other words, it's localized on the nitrogen here. But over here, the negative charge density can be delocalized into the ring. And so organic chemists are notorious. They don't show the lone pairs. We need to show the lone pairs here. And so organic chemists will show the lone pair when they want to try to show resonance delocalization. They got to show the lone pairs. And so here they're going to make a sacrifice and show the lone pair on nitrogen and how it can be delocalized in the ring. And how it can be delocalized in the ring is just what we did with phenoxide, which is the phenol, which is that alcohol, losing that proton. So here it's the same thing. Do you see how we can delocalize the lone pair into the ring? And this is going to make it less basic, a million times less basic. And so we delocalize it. And so one way of thinking about these benzene rings will have an electron withdrawing effect. Whereas a normal like cyclohexyl group will have an electron pushing. Because hydrocarbons are electron rich. So automatically when we think about hydrocarbons, so this is very odd because this is like a paradoxical type thing. Benzene burns very rapidly. It's electron rich. It's electron rich. Why is it being electron withdrawing rather than electron pushing? And it's because of the way the p orbitals are lined up here. And so it's paradoxical that it is an electron withdrawal being a hydrocarbon group. Does that make sense?
Yeah. I do have a question.
Yeah.
When you get into bigger rings, right? So let's just say like cyclohexyl, cyclooctet, right?
Yeah.
We have a segmented carbon ring, right? If you were to double bond each one alternately, would that decrease it by a greater magnitude than a million? Or would that be a less amount?
We have these big rings. You see these big ring structures?
Oh, look at those big constructions.
These are all sp2. These are flat rings. These are called porphyrins. And these ring structures have the electrons are delocalized over this entire big thing here. And this is just a small sampling of these. There's a huge number of these. These are called porphyrins. This is, many. These occur in biological systems here. This is heme from your hemoglobin here. Hemoglobin is what carries the oxygen in your blood.
I took biology a very long time ago.
So there's a huge number of these, and they're all delocalized. They're all sp2, sp2, pp. All the p's are perpendicular, and they all overlap. So you can have these huge structures like this. Not only that, they're like steroids and cholesterol. Look at cholesterol.
I love steroids. Very helpful. I've had a couple of shots.
You see these ring structures here. You can.
Are those
That's
all
not that
carbon-based
much.
rings? Are those all carbon-based rings?
Yeah.
I can only imagine that there would be a ring that's not carbon-based.
Yeah, this one's not. So, let's see the geometry here. This is sp3, sp3. These are sp2 here. It's not. This is not conjugated, where we have it. But there are others. I can't think of them right now. Ones, but porphyrins are a whole class of these types of big ring structures. And these are conjugated.
And these are, all the rings are connected by PP bonds, right?
PP pi bond.
PP pi bonds, yeah. But each one connected by the PP pi bond in the ring, right? As long as it's double bonded. Or does that apply to single bonds as well?
No, we don't have PP pi bonds for single bonds. There's one other thing. Let me talk about one other thing. One other thing is this. What is the hybridization on nitrogen here?
-2. Wait, that's oxidation state.
Need it.
SP3.
sp3. That's correct. Why? How did you determine if sp3 hybridized?
It's connected to 3 things over there.
And why did it sp3 hybridize? Minimize repulsion. A weird thing can happen though. And so let's talk about this weird thing. One thing is, what if we didn't hybridize it sp3? What if we hybridized it instead as sp2? If we hybridize it sp2, what is it going to look like? Well, we're going to have a nitrogen here. And then what we're going to do is we're going to put the 2 hydrogens in sp2 orbitals. So if we hybridize this as sp2, 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 and then where does the p orbital line up?
On the profile.
Yeah, perpendicular. And then take a look at what happens. Where are we going to put the lone pair? We're going to put the lone pair in the p orbital. Here. And the p orbital is located perpendicular, but this p orbital is also. This p orbital. And so if we sp2 hybridize that nitrogen, take a look at the lone pair can be delocalized into the ring. And so sometimes we see bizarre angles because we expected that to be sp3, but when you measure the bond angle, the hydrogen bond angle, it's 120 degrees. Not the 109 that you'd expect. And why is that? Because we do it for repulsions, but in this case, it might be more favorable to be able to delocalize the lone pair into the ring. And so there's a homework problem, which might fool you because you automatically think it's sp3, but it's actually sp2 because the lone pair wants to delocalize into the ring. Okay, so all right, so that gives you an idea. Now, what happens when we have a stronger base? A stronger base, a stronger base can more easily pluck a proton off an acid. And a stronger acid can more easily lose a proton to a base. And so the acid and base that we're going to look at is going to be water. So I think I'm done with this. Let me make sure. The only thing was Lewis acid base. I already did this reaction. Lewis acid base here. Didn't do that one. That's all right. Okay. Yeah.
I have a bit of a strange question. In a benzene ring where each one is connected by the pp pi bond, right?
Right.
Would there be a different name to classify the ring itself in the pp pi bond, or would it just still be like pp pi bond as a ring? Or I'm asking if there's a different classification because it's in a ring shape, or not, because it's still just the bond.
When we have it doesn't have to be in a ring. It could be in a chain. And if we have pp bi bonds that alternate, and then we have this, it's called aromatic. And so we can have aromatic rings and aromatic chains.
Oh, okay. So
The most important thing is, do we have, because you saw some of those rings had chains attached to it, and those chains are part of the whole aromatic system of delocalized pp pi bonds. And so we don't specifically look, because the structures can get a lot more complex than that. And so when we have alternating single, double, that's called a conjugated network. And the conjugated ring system is conjugated chains. They have special properties because of this.
thank you.
One of them is a stronger bond than you expect. Benzene has a stronger bond than what's expected. And the bond order in benzene should be 1.5, but the bond strength is a little bit stronger because of this aromaticity. So let's look at another power function, the pH. This is the power of the hydrogen ion concentration. And so sometimes it's easy to determine. Let's say the hydrogen ion concentration was 1.0 times 10 to the minus 1 molar. Then do you know what the power function is? The power function is just this. pH is 1. Now, we have 2 sig figs here. So we call it 1.00. This is 2 sig figs. In power functions, this is not significant. Not a sig fig. Because this comes from this. The stuff after the decimal point comes from this. Here. If we have 1.0 times 10 to the minus 7 molar, then what is the pH?
7.00.
Yeah, pH is 7.00. We call that neutral. This is acidic. In fact, this is strongly acidic. Here. And then if we have a 1.0 times 10 to the minus 14 molar, then the pH is 14.00, and it's basic. It's strongly basic.
Very basic.
Yeah. It could become even more basic, but When it becomes more, then the simple equations don't quite work as well. Okay, what if the coefficient is not 1? What if I have a coefficient that's not equal to 1? Then it's a little bit more complicated. So let's say I had a concentration of 2.3 times 10 to the minus 5 molar. So 2.3, this is, I'm getting close, 3, 4, 5, 6, 7, 8, 9, 10. If I go to 10 times 10 to the minus 5, that would be make the coefficient smaller, 1, make this bigger, 4. So it'd be 1 times 10 to the minus 4. So this is between 10 to the minus 5 and 10 to the minus 4. And so it's a little bit complicated. So what we're going to do is we just plug it into the equation. pH is the negative log of the H plus concentration or hydronium concentration. And so we just use a calculator for that to determine what the pH is. And so let's take a look at that. Although I don't know what's wrong with my calculator on my phone. I did an update and I can't get the scientific calculator again. So can somebody punch that out for me? Does anybody recall why pH 7 is neutral?
Because the amount of H3O plus and OH minus that water produces.
Yeah, that's right. That's correct.
The pH for 2.3 times 10 to the negative molar should be 4.63.
4.63.
And if you want to carry an additional sig fig, it's 8.
8. So we've rounded 4.64 pH. All right, so the 0.64 tells us this is 2.3. And the 4, well, this is between 4 and 5, so it's 5 in this case. 4.63. So in Chem 1B, you'll talk a lot about pH. So what we're going to do is we're just going to measure pHs. And we just know the lower the pH, the more acidic, the higher the pH, the more basic. pH 7 is neutral. This is at 25 degrees C. At different temperatures, the pH will change, but modern pH meters will have a way to adjust for temperature changes. All right, so did you guys check out? We're going to have to check out a pH meter. We're going to use the LabQuest pH meter, so you can work together or you can work alone if you'd like. This is a very simple experiment, and the measurements don't take very long at all. And so why don't you go ahead and check out the equipment, and then we'll get started with measuring some pHs.